Okay, welcome to videos on uh, VLSI design. So in this video, let us try to understand, okay, what is the time taken by an inverter to rise from 0 to VDD and VDD to 0. So basically we are trying to find out the expressions for the rise time, maybe the fall time, and also the propagation delay. So let us try to first define what is rise time, fall time, and propagation delay. Suppose if you consider, if you have this as an inverter having an input voltage something like this, and then we know that the output expected is something like this. You have an input 0, input 1, so the correspondingly you're going to have the output as 1, and the output is 0 for the corresponding inputs. So this is the input what you have at A. At B you have the output. Typically we will not have the inputs which are instantaneously changing from 0 to 1 within no time. So typically what we'll have is, we will have the timings will be something like this, which will have some definite time for propagation, sorry, a transition from 0 to 1. So assume that this is the input which is going from 0 to 1, having some time taken for the input itself to rise from 0 to 1. So correspondingly I am looking at what is the output of this. For this input, let us assume that the output of the inverter is coming out to be something like this, so for this corresponding 0, you have 1 as the input, and corresponding to this one, this is the 0 output. So let us try to define what is the propagation delay. So propagation delay is typically defined as you consider the midway of this transition. Assume that if it is VDD and if it is 0, you consider a point which corresponds to VDD by 2 at the input side. Similarly, at the output also you consider a point which is corresponding to VDD by 2. Now you try to find out the distance or the time difference between the transition of your input voltage at VT by 2, at what time it is crossing VDD by 2, and what time the output is again crossing VDD by 2. So this is typically defined as the propagation delay. Propagation delay of my inverter is now defined as the time taken by the inverter to have a corresponding output from half of VDD to the half of VDD on the output side. So this is how we can define the propagation delay. So coming to rise time, suppose you consider that again let us consider the same output voltage which is coming down like this, and then of course for the other transition it will actually go up like this. So ideally speaking, we will define the rise time and fall time as the time taken from for the output to change from VDD to 0. So this is the typical fall time, and of course you can see this is the typical rise time. These are all now you can see output is dropping from VDD to 0 volt, and it is going from 0 to VDD. So you are considering the 100% output voltage, that is 100% of the supply which is VDD. Again you are seeing that whether it is dropping down till to 0. But under typical conditions, capacitor will take long time to go to 0, and capacitor will take again lot of time for reaching VDD. So instead of defining the rise time and fall time as from 0 to 100% of VDD, 0% to 100% of VDD. So typically what how do they define the rise time and fall time as? Suppose if you consider this as the uh, a typical output of an inverter. So if you now you consider two reference points, which is one is corresponding to 10% of VDD. So this is VDD 10%, this is VDD 90%, meaning it is 0.9 VDD and this is 0.1 VDD. So now you define the typical fall time rise time as the time taken by the circuit or the device to go from 10% of VDD to 90% of VDD is denoted as rise time. And again, the time taken by the inverter to drop from 90% of the VDD to 10% of the VDD is now defined as fall time instead of 0% to 100%. Because if you wait till it goes to 0%, it may take long time. If you again wait till it is reaching up to 100%, it may take longer time. So typically rise time and fall times are defined as the time taken by the inverter to rise from 10% to 90% of the final output voltage, and again the vice versa for the fall time. We can also define the propagation delay as an average of this rise time and fall time. Okay, you can typically approximately write it as the propagation delay is typically half of the rise time, the average of rise and fall time. So this is the timing diagram of the inverters. So let us start trying to analyze. So what is the actual time taken by the inverter to give this rise time and fall time? So now let us consider an inverter having N and PMOS MOSFETs. This is VDD and this is VSS, or you can say it as ground. This is grounded and this is my input, this is output. Before we actually go into the inverter, we know that MOSFETs, whether it is NMOS or PMOS, so in case of a digital operation, they'll be either in cut off mode or either they are in uh, linear mode. So if the MOSFET is off, means we consider it in cutoff region. If the MOSFET is, this is for off, if the MOSFET is on, we will consider the MOSFET is in linear region. We will not consider the MOSFETs are not supposed to operate in saturation region in case of digital circuit. Typically, let us try to understand why the MOSFETs are not preferred to operate in saturation region in case of digital operations. Assume that this is VDS and this is ID. Let me consider this as my IV characteristics, the output characteristics of the MOSFET. If it is VGS now, so we know that this is the saturation region. So this is saturation. Of course, we have this. If VGS is less than VTH, we're going to have almost zero current. This is the saturation region. Okay, now this is saturation, and we call this as the region corresponding to linear region or triode region of operation. So when we have these three regions of operation, MOSFET is not recommended to operate in this saturation region, because saturation region corresponds to a resistance of very large value, ideally speaking infinite value, which is not recommended for a MOSFET which is a part of your inverter. Assume that if you have a load capacitor CL, if this MOSFET is operating in saturation region, so we know that the capacitor which is there here, if it has to charge through charge to VDD through this resistor, which is, we call it as RP, if the resistance is very high, it takes a very long time for this capacitor to charge. So we are not supposed to have this value as large as possible. It is not recommended. The value of this RP should be as small as possible. And of course, similarly, if the output has to discharge, if this voltage has to become zero, then it has to discharge to this transistor. Again, the resistance offered by this should be as small as possible. That is possible only when the MOSFET is operating in linear region. So that's why for any digital operation where we are considering transition from 0 to 1 or 1 to 0, we need to have the corresponding resistance of the inverter. Okay, we know that while if the output has to go to high, it is the RP which is responsible. If the output has to go low, it is the RN that is responsible. So they have to be as small as possible, so that we're going to end up with quick charging and quick discharging, so that your TR and TFs will be less, which will going to end up with a lesser propagation delay. So all these things are less if Rn and Rps are less. Rn and Rps are less. So since the RL and RPs have to be less, so they have to be operating in this linear region, because you can see the slope is finite here. Here the slope is almost 0. Since the slope is 0, the resistance is very high, which is not the desired thing. So the MOSFET has to operate in linear region for its digital operation. So let us try to find out what is the expression, what is the typical expression for the on resistance of the the MOSFET. So we know that ID in linear region is given by half Kp W by L 2 VGS minus VTO into VDS minus VDS square. So this is the typical expression for the drain current in linear region. So since we are considering the MOSFET operate in the lower values of VDS, so VDS is naturally a very less value, so that you can actually neglect this VDS square can be totally neglected, because VDS itself is less, then square of that lesser quantity is still very less. So that now this equation reduces to ID is now almost equal to half Kp W by L. Now I can see it is 2 VGS minus VTO into VDS. So okay, you can certainly neglect this. So we know that the resistance, okay, let me call it as, whether it is for NMOS or PMOS, it is almost the same expression except the sign. So resistance is now given by VDS by ID. So since it is VDS by this expression, we will end up with R is equal to, so half Kp W by L. Of course this half and this 2 will go off, so you'll end up with VGS minus VTO. So now I can write R is equal to 1 over Kp into W by L VGS minus VTO. So this is the expression for resistance of either NMOS or PMOS whenever it is charging or discharging. So whenever it is charging, it becomes RB. Whenever the load capacitor has to be charged, so it is through RP. If that load capacitor has to discharge, now it has to discharge through Rn. So let us try to understand what happens to this resistance R if you increase the dimension. Suppose if you scale it up, when I say scale it up, you increase the width of the transistor, or W by L is actually increased. When the W by L is increased, as per this particular equation, as you increase the dimension of the MOSFET, especially the width of the transistor, then resistance is going to come down. So as you increase W by L ratio, the resistance of the MOSFET, which is responsible for both charging as well as discharging, will going to be reduced. So now we could able to get a relationship between what is the resistance offered by a inverter as you scale it up or scale it down. If you scale it up, then the resistance will going to come down. Simultaneously, let us see how does the capacitance will going to be get affected due to the scaling. When I say scaling, you are trying to increase the dimension. Okay, we know that this is an NMOS transistor. Suppose if you take this is a cross section, this is P minus substrate, and then you have, this is your N plus, and you have this as your N plus. You've got an oxide with which you won't have, this is your gate structure, source, drain. Suppose if you basically see, this is your bulk. Suppose this is NMOS, you won't have capacitances or C of the MOSFET. C of the MOSFET, as we discussed in the earlier videos, is due to oxide capacitance plus the junction capacitance. So this is the capacitance due to oxide and capacitance due to junction capacitance. This is typically how the capacitance can be divided. So this is, you can see now it is between CGS, this is CGD, then between drain and the bulk you have CDB, and then you have again CSB. So these are the typical capacitances associated with this particular MOSFET. So when I say capacitance due to oxide, it is given by COX, which is the per unit area capacitance multiplied by the area. So area matlab here it is the width on the suppose if I say this is my cross section view. So now this happens to be the length of the transistor and this is the width of the transistor. So you have this oxide layer across this structure. So it is now given by COX W into L. Then we know that C junction is also given by it is C junction, which is per this is farad per meter multiplied by of course again it is proportional to the width of the transistor, where you have the perimeter, all those parameters coming in here. I can see here also you have Cj which is junction capacitance, which is per distance multiplied with the width. Now what is we are basically trying to note here is how does this MOSFET capacitance varies with the dimension. Suppose if you increase the W by L ratios, if you increase keeping this W constant, if you simply increase keeping this length constant, if you are increasing W, so this W by L ratio increase. So if W by L ratio increases, does this does this oxide capacitance increase? Yes, as W increases, because this is constant, this is going to increase. As W increases, this will also increase. So as you increase the dimension of the MOSFET, so the capacitance offered by the MOSFET, that is parasitic capacitance, this suppose if I say CT, which is C total, will also increase. C total will also increase. So what we are actually trying to find out is, so how does the scaling will affect the scaling? If you scale up the transistor, the capacitance will increase, whereas when you scale up the transistor, the resistance will reduce. So let us use this analogy and try to find out what is how it is going to affect my rise time and fall times. So let us consider an inverter having certain dimension used to drive nothing. So assume that it is not at all driving anything. So when it is not driving anything, let us see. So this is your V naught, this is V in. So this is a PMOS transistor, this is NMOS. You can see I'm going to have a capacitance corresponding to this. I'm going to have one more capacitance. I'll have a capacitance here. Of course, this is your bulk. You're going to have one capacitance corresponding to this. And then you have a bulk for PMOS. You have this capacitance. You have this capacitance. Of course, we know that there is a capacitance existing between output and input, which is CGD of NMOS. Again, there is one CGD of PMOS transistor. Using Miller's theorem, we can certainly split this floating capacitance into capacitance which is there from drain to ground. Of course, this is also usually grounded. Drain to ground you have, and again you have from gate to ground. So if you have a look at this one, this is the actual capacitance that you want to end up with. So this you can further rewrite it simply by only two capacitances. So I can able to represent the entire inverter by only two capacitances. One is what is C intrinsic at the output side, and what is C in. So this is C in. So there is an input capacitance seen here, which is effectively CGS of N plus CGS of P transistor. So you have a CGS of this and you have a CGS of this particular N and PMOS transistor. Because these two are coming in parallel, they're going to add up. So C in, the input junction capacitance, of this inverter is the capacitance between gate and source of NMOS, between gate and source of PMOS transistor, they have been get added up. And how about the output capacitance? C out, even though you are not connected exclusively any capacitance here, because of these because of these that Miller capacitance and because of these junction capacitances, I will end up with lot of junction capacitance, plus of course there is Miller capacitance part of the oxide capacitance. So here you're going to have, I will write a C out as nothing but C intrinsic. So ultimately, even without connecting any load capacitor, you have something like this. So effectively, what are the resistance offered by this? The resistance offered by this is Rp. The resistance offered by this is Rn. If you try to find out what is the, now you are considering a load capacitance of C intrinsic. Can you see now there is a time constant corresponding to rise time, there is a time constant corresponding to fall time. The time constant corresponding to rise time is Rp into C intrinsic, because it is this capacitor you are thinking of charging, and again it is Rn C intrinsic. So these are the resistance and capacitances which are responsible for rise time and fall time. Now let me just scale it up. So what do you mean by scale it up? Let me increase the WBL of this and WBL of this by S times. So I'm just increasing the WBL of this and this by S times. So as we know that since it is increased by S times, the resistance, suppose if you want to know what is the rise time after scaling up, so after scaling up it is now, you can see Rp by S, because as we saw in the previous case, so as you scale it up, the resistance will reduce. By how much you increase, by the same amount it will reduce. So here we are considering the scaling up by S times, and then that will going to reduce your Rp by S times. Similarly, we also saw that if you increase the dimension, the C total will increase proportionately. So now it is S times C intrinsic. So basically what you can see is, if you scale up the transistor by any amount, the resistance will reduce by S times, the capacitance will increase by S times. So effectively it is Rp into C intrinsic, meaning the scaling of the transistor will not affect the rise time and fall time of an intrinsic inverter. What do you mean by intrinsic inverter? Which is not connected to any load. If you're not connecting any load, this is how it is affecting. So it is, the scaling will not affect at all. Then what is your fall time? Fall time is also Rn into C intrinsic. Rn into, so this is Rn is the one which is responsible for discharging. That's why it is R into C intrinsic. So basically what we are trying to understand is, scaling will not affect my rise time and fall time. Okay, let us try to get a exact expression for the rise time and fall time. So since we consider the rise time as the time taken from the, for the capacitor to rise from 10% to 90%, so what I have is something like this. Now this is, now I'm writing, I'm representing the equivalent resistance under no load condition. So under no load condition, what I have is, this is my C intrinsic. This is not an external capacitance. This is the capacitance offered by this MOSFETs. This is VDD. This will call it as Rp. This is my Rn. So let us consider the rise time of it. So we know the capacitor equation as, now assume that if it is charging like this, so it is Vc, that is capacitor voltage, is nothing but V final minus V initial e power minus T by Rc. So in this case, R is equal to Rp, C is equal to C intrinsic, and whenever your Vc becomes 0.9, because now you're thinking of charging, whenever it becomes 0.9 of VCC, then I will say T is equal to TR. Corresponding rise time, okay, you can see now, suppose if this is your input, sorry, if this is your input which is going up like this, so we know that this corresponding to this will going to have a zero output. When the input is coming down, output will rise up. Now it is from this 10% to 90%, you are looking at 10% to 90%. So since it is, it is the duration from 10% to 90%. This is my rise time. So let me find out what is the time taken, that is TR. So VC is now 0.9 times VDD. Let me write it as VDD here. And V final, as t tends to infinity, we know that the capacitor will charge up to VDD. And V initial, let me consider V initial as 0.1 times VDD. 0.1 times VDD. And of course R is equal to RP, C is equal to C intrinsic. If I substitute that, it is 0.9 is equal to 0.9 VDD is equal to VDD minus VDD minus 0.1 VDD e power minus TR by R. This is RP into C intrinsic. So we will get an expression upon solving this. Suppose if I just continue the expression for this. So have it as 0.9 VDD minus of VDD is equal to minus of 0.9 VDD e power minus TR by RP into C intrinsic. So now this is minus 0.1 VDD is equal to minus 0.9 VDD e power minus TR RP into C intrinsic. So you can cancel out this negative sign. You can take out this VDD also. Now it is 0.1 is equal to 0.9 e power minus TR by RP into C intrinsic. So upon solving this, you can get the expression for TR as equal to RP into C intrinsic, into ln of 9. So this comes out to be the rise time is equal to RP into C intrinsic into 2.2 times. So you can write TR is equal to 2.2 RP C intrinsic. This is the expression for the rise time whenever it is rising from 10% to 90%. Similarly, you can get an expression for the fall time, which is TF is equal to 2.2 times R N into C intrinsic. Rn into C intrinsic. This is the time taken for going from 10% to 90%. So this way we can able to get the expression for the rise time and fall time if you are not considering any external load capacitance. Suppose if you consider a load capacitance, we should try to find out what is the overall time taken by your system to go from 10% to 90%. That we'll see in the next video.